All right. How's it going, everybody? Just checking the live looks good. I can see my playback coming through, so that looks squared away. We'll give this a few minutes to get started and let some folks join in before we kick off the topic of discussion for this evening. I like it, so it goes along with it. So I am in the process of pulling up the design zone stuff that we talked about last week. So no problem, Alpin, no problem. Just glad you guys are able to join in on the fun. So at least that's what I'm hoping we're doing, is having a little bit of fun. So we'll give this another minute or two to get started, and then we'll dive into some of the technical content and things like that. If you guys have any questions, comments, feedback, that type of stuff, something you would like me to cover, drop that in the comment section of the chat. I will see it, and I will pull that up and take a look at it as we're going along here, and get this party started here. Just a minute. I was going to give everybody a couple of minutes just to get in, because I don't want to just dive right into the content, and maybe there's a question you might have or a topic you want me to dive into, stuff like that. I know Alec was looking for some details on the interconnection between the distribution switches, so we'll talk a little bit about that. We're going to talk a little bit about SDA and how that comes into play, so we're going to take that into consideration as well. So, but not limited to those things, right? So if you guys are like, hey, I've got this situation and stuff like that, I'm happy to try to help answer those questions, things like that. And that's kind of why I'm here, right? Am I a CCDE? No. But have I designed a lot of networks? Yes. Have I broken a lot of things? Yes. Have I fixed a lot of stuff? Yes. So I feel like I'm kind of qualified to be here. So we'll wait till about the 4 after. I see there's 8 viewers currently. Well, it keeps going up and down, so I'm assuming that we're going to get a decent amount of people to show up. So we'll get going here in just a moment. So anyway, like I said, if you're joining now, if you guys have a question or a particular topic that you would like me to dig into, stuff like that, let me know. The chat is a little bit delayed, so if you're I haven't actually timed it. Maybe I should do that. Where's the clock? Where is the clock? How do I show? I used to be able. Oh, is that the clock? No. There used to be a way for you to hover over the clock and it would tell you how many seconds something is taking. Maybe I should just time it. I have a feeling it's about a 10-second delay between when I move my arm and when I see it show up in the live stream. So I think it's about a 10-second delay. So I'm actually eyeballing the video on it right now. That's about 10 seconds there. So maybe 15, 20, or longer. Anyway, we're at the 4 minute. Okay, so we're 4 past the hour. So I'm going to go ahead and get started. So, so this evening's discussion. Okay, so yeah, it was about a 30-second delay. So from last week's discussion, so I just deployed a new 9500 core a couple hours ago. I just wanted to say some of that topology talk last week was some good topology info before our deployment. Good, man. Good, glad to hear. That's my goal, right? Is to have you guys run into stuff and hopefully head off problems before they become a problem, right? So I'm glad to hear that. So let's go ahead and talk a little bit about, since the first question came in was from Alec, let's go ahead and take a look at what he's talking about. Since you'll talk about 2 and 3 tier design, could you please explain about distribution switch interconnection, depending on what link between them should be L2 or L3? So what he's basically asking is, and I'm going to pull up the big real world networking topology that I showed you guys in a previous video. I've been working on like some of the way that it looks to try to make things a little clearer. But essentially what Alec is talking about here is if we come down here to the distribution layer, right, which is this pair right here. If you notice between switch 78 and, did you get a chance to work out today? No, that will happen after I'm done with this live. That'll come later. I'm going to get it in though. So definitely going to work out, that's for sure. Okay, so let's go thin line. So what Alec is referring to is this link right here, which is the link between the distribution distribution switches. And the question is, when should you use that for layer 2 versus layer 3? And it depends, right? So typically speaking, if I have a layer 2 requirement where this is running, and we're going to assume that these are 2 physically different devices, meaning there's not a stack-wise capability going on between them or anything like that. So this is a pair of, say, 3750 X's, and they are running, you're doing HSRP, so hot standby router protocol, between the devices in order to do first hop redundancy. So all of your VLANs, and let's say that there's 10 of them down here, let's say we're pinning 5 VLANs here and we're doing 5 VLANs here. So we're trying to make both switches active for 5 VLANs and active for another 5 VLANs. Now, this would be a great scenario where if this is what you have deployed, where you'd want to port channel these guys together, and you would want to make this port channel a trunk link. So this would be a trunk. And you would be port channeling these guys together, probably 10 gig link between the two. So in case there's a scenario where you've got traffic hitting switch 78 and it needs to go to switch 79, it could go up the path. And the reason why you would do it this way is actually very, very simple. If you were to have a scenario where these links all died, or the switch dies, that's actually more realistic, is the switch as a whole goes down versus your fiber runs, your structured cabling between your switches were to fail, you're more likely to see a switch itself die. But let's say, for the sake of argument, that that's not the case. Let's say that this interface right here dies, and this is still your egress point, right? And let's flip it over here, back to yellow-green, and you still got a default route going that way, or whatever your routing design is. Well, what's going to end up happening is if PC93 here is in, say, VLAN 10 that's pinned to VLAN switch 78, that traffic is going to come up here and then across the inter-switch connection and then out to the internet or wherever it's got to go. That's going to be the traffic pattern. Where if I've got PC95 here, well, let's do 96 because we're going to say VLAN 10. PC96, he's going to take this path directly to 78 and then out to wherever he's got to go. And why is that? Well, the uplink between switch 80 and switch 78 has now been cut. So therefore, spanning tree on switch 80 has to reconverge, right? And we're assuming that we're using rapid spanning tree protocol to reconverge and send the traffic out towards switch 79. So that's if you're using all individual devices where there is no chassis aggregation. So you're not using VSS or virtual switching system. You're not using Stackwise or Stackwise virtual or any of that, those new whiz bang wow capabilities. Actually, none of them are really new. VSS and Stackwise have been around forever, but you're not leveraging chassis aggregation like you would, like if you had two physical devices and you were to cable them together like this, and this is your Stackwise cable. Well, if you're doing that, that's supposed to be a W, by the way. If you're doing this, then this right here, HSRP, completely goes away. And you might ask, well, why would it go away? Well, it might go away because you're not going to run HSRP on, you need two physical devices to do any type of gateway redundancy protocol. HSRP, VRRP, GLBP. You need two physically different devices that aren't sharing the same control plane. So that's where that would come into play. Now, for the layer 3 piece, what would be a great scenario for layer 3? Well, a layer 3 scenario would be you would also put these guys into a port channel, but you would do underneath, say, port channel 1, for example, you would type in the command no switch port. And what that's going to do is it's going to convert a layer 2 port channel into a layer 3 port channel. And then you would do routing between these guys. So if something were to happen, these guys are the default gateway, and you're still running some sort of first hop redundancy, right? HSRP, well, let's say for VRRP for this case. And you have a scenario where your 5 VLANs are pinned here and 5 VLANs are pinned here as your gateway. What happens then? Well, if a link goes down, it's not that big of a deal, right? You come up here and the gateways are shared, right? But au contraire, can they really be shared? Will that still work? Like, how would you run VRRP if this link between the two switches is a layer 3 link? Well, that's not a problem because you're sending your messages for VRRP, anything first hop redundancy, are going out your LAN links and vice versa. They're going out this way. They're not coming across the interswitch link connection. They can if you're running layer 2, but you can run any first hop redundancy as long as you've got connectivity between your LAN switches, then you're okay. So that would be the caveat. So if you're coming up here, what will end up happening is if you're doing VRRP in that specific example, what will end up happening is if this link was to go down, what's going to end up happening? Spanning tree on this guy right here is going to reconverge. So RSTP is going to say, don't use gig 00, use gig 0/1. It's going to come up here, and because this guy happens to be the VRRP peer, right? He might be even standby. But in that situation here, you would actually need to start being a little bit more granular in your VRRP design because you'd have to start tracking physical link at that point. Because if you decide to do layer 3 on your interswitch communication, you no longer have the flexibility of trunking your data to the other switch. That feature goes away. Do you need the aggregate if you just load balance on OSPF? The aggregate meaning this port channel between the two, or are you talking like a summary? You have to clarify that for me. So since you lose the flexibility of being able to float the traffic over to the other switch, you need to be able to converge here and send the traffic up to the right egress point. That's what's going to end up happening. So so if I have a customer that wants to do first hop redundancy and they're going to be doing a pair of switches where they're connecting the two together like what we already described, I'm going to keep this guy right here layer 2 so that we can have traffic flow across the interswitch link. If we're not worried about that, whether they care or not, whatever the situation is, I'm actually going to go, in most cases, I'm not going to do a layer 3 port channel. Now, what you can do, and this is kind of an interesting scenario, is you can actually keep this as layer 2, but enable OSPF or EIGRP or whatever protocol you want to, you can run that peering over the interswitch link, right? You can run that with over your SBIs, and then you could theoretically still have traffic go this way. So having, oh yeah, no worries, the port channel. So that's actually a good question. No. So what Noah's asking is, do you need the aggregate if you just load balance on OSPF? And the answer to that, I'm going to say no, you wouldn't. So you theoretically could say, let's scrap the interswitch link altogether, right? You could say, to heck with it, and you're just going to use the uplinks right here. So this guy here and this guy here, right? You could do that and get rid of the interswitch communication and then still provide VRRP or some sort of first hop redundancy between the two switches. That would still theoretically work. And I can't think of a reason why it wouldn't, because then you'd be getting a route this way, you'd be getting a route this way, and you'd still be able to get out to wherever you got to go. There just wouldn't be any inter-distribution switch communication. And that would work, right? Is there anything wrong with it? No. Is one way better than the other? I mean, there's three potentially ways that you can do what what we've already discussed. So, in my opinion, I would still probably go the layer 2 trunk between the switches route. That's just because I'm very, very comfortable with it. And a lot of times that's going to be the direction a lot of people go anyway. They're going to stay within their comfort zone, because if something breaks, like in Noah's case, it's 2 a.m. where he's at. If I get a phone call at whatever time, I don't want to sit there and have to try to figure out what's going on in the middle of the night when something's broken. That's the last place you want to be. So that I'm going to go with the design that I'm comfortable with deploying and supporting. Now, if, let's say, for example, there's 4 of us in a conference room and 2 of us want to go one way, one guy wants to go the second, and a third guy wants to go with what Noah's describing, where we don't have the aggregate, we do our first hop redundancy between the switches, and then we have a default route, or we load balance up between 74 and 75. Would that work? They all would work. You just have to understand the operational piece of it when it comes down to reconvergence and how that would work. So now, what is the likelihood? Let's say out of 100 failure events over the lifetime of your network, how many of those failure events is going to be a physical interface going down, structured cable failing, that type of stuff, versus a switch blowing up because it just dies power, SFP fails, any number of stuff like that? I'm going to say the likelihood of that is probably going to be 1 or 2 out of 100. At least that's my experience. I've seen more hardware, more switches themselves fail than I have seen physical interfaces stop working. It happens. That's why I said 1 or 2 out of 100. But that's why I see it the way that I do. Now, some people might argue against me. That's okay. You're entitled to your opinion. I have mine. And, it would be one of those things where if somebody was to sit there and bring up a couple different ways of doing it, it'd be like, okay, that theoretically would work. And what I would do, I would do my due diligence, right? I would spin up a lab similar to what I have here, and I would test them all out. Because I'd want to understand the intricacies of, if I do this, then this is going to be the aftermath. And then I would have a solid understanding of what's going on. And that's the engineer, right? That's what the engineer is supposed to do. They're supposed to make sure that they understand what is being done, how it's being done, all that type of stuff, so that when things do pop up, they aren't sitting there going, I don't know, Steve. They're able to figure it out and get it working again relatively quickly without, trying to pull their hair out at, 3 or 4 in the morning. There's no fun in that. I've been there more times than I wish. So hopefully that, Alec, I don't know if you're on or not, but hopefully that answers your question and the reason why I would go the direction I'm going. I would say that there's not a... the universe is not pulling me one way or the other, but I have more of a comfort zone with leaving the aggregation link between the two switches, layer 2, just so that, and you can run layer 3 across it, but running pure layer 3 where there's no trunking capability between the switches, I usually steer away from that. And the reason why I do a lot of the time is if you look at, think of like Nexus with VPC. And I'm going to scroll down here actually a little bit because I actually have a VPC design set up down here at the bottom. So think of a Nexus VPC design, right? You have two Nexus switches. One of these ports is going to be the peer keep alive, and these other two ports are going to be the peer link. You're going to configure the peer keep alive in a VRF so that it can be either a management VRF, or you're going to create one so that the switches know that they're there. You're going to create the peer link so that they're able to exchange information back and forth between each other. And then these two interfaces right here are actually going to be bundled together into a port channel. And then you're going to give it a VPC ID. And then this down here is going to be placed into a port channel as well. So in this particular case, you have to do a layer 2 link. You don't have any choices about it because that's the VPC design. You don't have the ability of doing a layer 3 link. Can you route over the links? You can. I've done it. It does work. There's really doesn't seem to be any problems with it. But when you have SVIs configured on your switches and you're routing over the top of them, it gets the job done because you don't have the choice of making these two switches. Theoretically speaking, it's chassis aggregation, but the Nexus methodology, where VSS and Stackwise Virtual make two physical devices like this, right? You link them together with a cable, Stackwise cable or fiber, and that makes them look like one big box. It makes them look like basically a switch with two line cards in it, right? So this is the physical, this is the logical. Nexus does the exact same thing with VPC. You have your two switches, and what it looks like is this. You have two physical devices, and it looks like there's a port channel sitting between the two of them. So the two switches look like one because the VPC configuration comes into play to make that look the way that it does. So, but it's two physical switches. You log into each one individually and configure it. Where on VSS and Stackwise, when you're logging in, you log into whatever the master switch is, and you make your configuration, and you'll see like 1/0/1 through 48, and you'll see 2/0/1 through 48, so on and so forth. So that's a two switch stack. And I've seen 7 or 8, I think is the biggest I've ever seen. And when I saw that, I was like, we're not doing that, guys. I broke it up into two different stacks just for the simplicity of the fact that, these switches don't have big horsepower CPUs in them. So when you've got, a few hundred MAC addresses being learned, that's going to slow things down if you've got lots and lots of VLANs. I'm not a very big fan of having really big switches for the sake of having really big switches. That doesn't make any sense to me. If you're going to do it, modularize your design. So if you have, let's say you have your, 1, 2, 3, 4, 5, 6 switches, I'm going to say, okay, that's great, but instead of having 6 switches, let's break that into one big stack. I'm going to break that into 2 stacks. I'm going to have 1, 2, 3. I'm going to have 1, 2, 3. And then I'm going to draw a box around these guys just so that it's easy for you guys to understand. I'm going to link these guys together a bunch of different ways. Probably from line card 1 to line card 1 and the line card 3 to line card 3. I'm going to port channel these guys together so that anything that's downstream of them is going to connect to both. You're giving yourself physical node redundancy. So if a switch dies, if let's say switch 3 dies here and switch 3 dies over here, then you still have uplink connectivity between line card 1 and on both switches. That's how I like to do things, and in my opinion, you're increasing your fault domains, right? If there's a problem in the network somewhere, you've got 2 cores to deal with, not one core with 6 line cards in it or 6 individual switches making up your stack. I go like that, and when I explained that to an architect a long time ago, he goes, that makes a lot of sense actually. So, because he was going to do one big line card and have everything hook into it. He was going to, was it 4 or 5 floors, and he was going to bring everything in from the different floors into each switch, so that it made it easy to understand who was where. Cisco told me it's more cost effective to get a chassis once you start going over 4 switches in a stack. It might be. I've never really looked at the numbers, but I wouldn't be surprised at all if that was the case. But that's essentially where I like to go with it because it gives me more redundancy. And going back to the point where that guy was talking about how you take, say, first floor, the first floor switch, second floor. Well, you can run them to each stack, right? And the job gets done. It's no different than plugging them all into the same two different switch stacks for each switch into two different switch stacks switches in the switch stack. So that's essentially how I like to look at it. Is there anything wrong with that? I mean, like I said, the one thing about network design that has always been troublesome for a lot of people is the fact that it's subjective, right? Everybody, for example, right now when I'm looking at, there's 10 people watching this live, and 10 of you, well, 12 now that I'm watching. Let's say there's 10 people in a room, and all 10 of you know the exact same information, right? But 4 of you are looking at one way, 2 of you are looking at another way, and then the last 2 people have their own ways of looking at it. So you have 4 different viewpoints on the same bank of information, and it's up to all of you to come to a common agreement and move forward with the design, right? So that's why when you look at how stuff is put together, you have the technical piece, and then you have to be able to justify why you think you should be able to go a certain way. And it's not really an argument per se. It's more of okay, this is why I think we should go the way that we do. And then a lot of times it comes down to a vote. All in favor of Rob's way. You might only get 2 people to hang out like, okay, I guess, you might have articulated it well and done even a whiteboard session to plead your case. But then somebody else comes along and you're like, oh, okay. Maybe they say something you hadn't thought of, So there's lots of different ways to do the job. It really just comes down to, everybody coming to a common agreement on it and getting stuff into play. So hopefully that answers your questions and provides you guys with a little bit of insight on how stuff gets done. And to Noah's point, it might be more financially, it might make more financial sense to buy a chassis versus individual switches. But I don't know. And here's my opinion on chassis versus switch stacks. With a switch stack, you're limited to whatever the platform's capacity is, right? So if you have a scenario where you've got a switch chassis, let's say you've got back in the day, I haven't touched the new 9Ks yet, very little 9500 config. So I'm going to go back to the old school where the 6509 was a very popular switch, even though they're being sunsetted and retired because they're just old now. Was this fine? Sure. I can't tell you how many supervisor engines I've replaced. I can't tell you how many line cards I've had to replace. And I don't remember the specifics because it's been probably 9 or 10 years since I really messed with one. But what I can tell you is the chassis itself, right? You have the chassis and then you have the line cards that go in it, and then I believe it's at the bottom is your power supplies. No worries, man. So, if and on the back side of the switch, if we were to draw it out a little bit to make it easier to look at, like the back panel here, right, is what they call your crossbar fabric. Well, in a situation like that, if something happens with your line card PCIe or PCI, I'm not sure which way they refer to it, if something goes sideways with the contacts on the back of that line card is now dead. Wanted to ask you if you could touch on fabric path. I mean, I could talk a little bit about it. It's been a long time since I've messed with it, but if you got a question about it, I can try to answer it. So that's that to me, that is the drawback to a chassis-based platform, where if you stick a line card in and the contacts and the crossbar and the backplane get goofed up, then you've got to replace the entire chassis. Where if a switch dies, all you got to do is pull it out of the stack and put a new one in and cable it up, and away you go. So, well, not exactly away you go, but I mean, there's a process to it. But that's essentially where that piece comes into play. So, anyway, that is that's really the caveats that I wanted to mention when it comes to stack-wise versus or chassis aggregation in general. So if there's any questions on that, throw them in the comments section, and we can talk a little bit about other stuff if you like. I know Matt there just asked about Fabric Path. I will try to explain my understanding of Fabric Path. It is, I believe it is only supported on Nexus 5Ks. And you would run Fabric Path. Let me think here. I haven't configured Fabric Path in a really long time. I'm trying to think back. You'd have to turn the feature on, so feature Fabric Path on both devices, and then when you do that, then you'd have to put these to type fabric type or port type fabric, something like that. And the way Fabric Path was explained to me back in the day was you would it was conversational, meaning it would only advertise things that it knew about. Kind of like how Lisp works, like almost DNS-like in its operation, where if you didn't need to know the information, it wouldn't hold it. But beyond that, I'm trying to think back to how Fabric Path works, and I'm having a hard time remembering because it's been so long since I've worked with it. I can tell you more about Fabric extenders and fexes than I can Fabric Path, but that's pretty much my limit of Fabric Path to how it works. I'd have to go back and read up on it, but so considering I mentioned Lisp, locator ID separation protocol is for those of you that are familiar with multicast and how PIM dense mode works versus how PIM sparse mode works, and you've got BGP and how it operates. BGP is very much like dense mode, and Fabric Path is very much like sparse mode. And the difference between the two is in BGP, once a route is learned by BGP and then propagated, you get it whether you need it or not. Dense mode is the exact same thing. It's assuming that there's a dense population of multicast receivers, and it's going to go ahead and propagate the multicast traffic everywhere, even if there's no receivers on a particular segment. And that's why you have that prune timer that kicks in every 3 minutes and tries to prune the multicast feed back away from the receivers that don't exist. Where Lisp works much more like sparse mode, where sparse is assuming that there's not a lot of multicast receivers, and you're going to deal with scenarios where the receiver has the signal with IGMP to the first or last hop router, which is going to be closest to the receiver, and that's going to flip that IGMP report message from a report over to a PIM join. That message is going to go to the rendezvous point. The rendezvous point is going to then connect the shared tree to the source tree, and then once that happens, then communication will begin to flow from the source to the receiver. So that's the high level of how multicast works with PIM sparse mode. So Lisp is like that, where if you need to talk to a particular device somewhere else in the network, it's going to go out to the map resolver and the map server, and it's going to say, okay, who owns, how do I get to X route or X subnet? Or I believe they call them endpoint identifiers. Because you have, your RLock, your routing locator, and your endpoint identifier. And so you're trying to reach an endpoint, and so Lisp will figure out, okay, which router owns that subnet, and then how do I forward to it, right? So that's where that comes into play, and that is why software-defined access leverages Lisp versus BGP. Now, what's interesting is inside of the data center over here, I'm going to erase my circle, you don't use Lisp in the data center, you use BGP. Why do you use BGP? Well, because the fact that you're going to have external connectivity out to the other parts of the network in order to get traffic in and out of the fabric. I don't know how they do that in SDA. I have zero experience with deploying SDA, but I have a crap ton of VXLAN EVPN deployments under my belt, so I can speak in finite detail about how that works. But Lisp is the control plane, so it's going to figure out who needs to talk to who in that respect. And when I read up on why SDA uses Lisp versus BGP, it made sense, right? It's in my opinion, and I've got nothing against Lisp as a protocol, but and I think I've said this before in videos where I don't understand why Lisp was even created. To me, it was a bunch of smart people, a bunch of smart engineers, I believe from Cisco, dreamt up a protocol that works similar to DNS, and they created a solution for a problem that didn't exist. That's my take on Lisp. And and since then they have been Lisp has been trying like I refer to it as has been an orphan protocol, meaning that it doesn't really have a place in the network unless it had to be like put somewhere, and SDA is where it was put. So I'm not aware of any very large or even any very small Lisp deployments. I have labbed it up just to see how it works and stuff like that, just to test it out, because it was on the old service provider blueprint. I labbed it up, I tested it, I understood how it worked, and I got it working. I took it all the way to the end of the earth, where as far as you could take it, with a book that was written, I think it was by Cisco Press. It's not bad. It gets the job done, but in my opinion, it is I don't understand why it was even created. So it works very much like DNS. You have to go out and ask for something, you get a response back, versus the flooding style design of all the routing protocols, right? All your IGPs and BGP, what do they all have in common? But they all have the same common thing. They all will take whatever information that they know about and they will push it to the rest of the network. So it's like dense mode. You're going to get it whether you need it or not. So maybe that was an optimization to try to rewrite routing protocol history. Been pulling out fexes all last year for a new ACI deployment, but still a cool, cost-effective solution. Yeah, fexes, yes. Okay, so for those of you that don't know what a fex is, a fex, also known as a fabric extender, and I have had the unfortunate experience of deploying lots of fexes in a lot of different designs. So the fex was kind of a retarded switch. That's how I'm going to put it. It literally does not learn anything, and that's why I call it retarded. So the idea here is you have a parent switch, which could be, this could be a 7K. That's funny. Your senior architect calls those smart engineers Cisco's basement children. That's pretty accurate. 5K and 9K. So you could take any basic model of 7K, and that was what they refer to as your parent switch. And what you would end up doing is you would turn the feature on, and then you'd have your switch, and you'd run, I'm trying to think, was it 2? Yeah, you'd run links down to your fabric extender, and the fex itself could be either Ethernet or it could be SFPs, depending on the design or the type. And what you would do with that is think of it like a Meraki switch, right? You can't console into a Meraki switch, and you can't console into a fex. The fex ports would get powered on, and then the parent switch would detect the fex. It would download its config, and then you'd have to give it a fex ID, so like 101, and then or 102, and then what you would do is you would have like 1 through 48. So it would be a port number, logical port number on the parent switch. So you would go in, you would configure 101, 1 through 48, and it would be configuring all the ports on this particular switch. That's what a fabric extender's job is to do. And you could do things over the top of it. You could do VPC over FEX and things like that. Matter of one of my last deployments, I'm sorry, one of my earlier deployments at my last job, we had 4 FEXs, something like that I had to stand up on a pair of 9Ks, and it was like, I didn't even know they existed until I was 90% of the way done with the customer's migration. I had done, a few months worth of work trying to get them where they were going to be, gotten their entire fabric up and running, had a bunch of other stuff done. They had been swinging cables all night, so like from 9 o'clock in the morning until 10 o'clock at night. And I was, I think I was probably pushing 18 or 20 hours on this migration from the old to the new. And it was funny because their senior engineer is like, okay, we need to get the FEXs stood up. And I looked at him kind of like, excuse me? What FEX? And so we had to figure out the cabling on the fly. And so we plugged them into a pair of 9Ks. I think they were 93 180s, and get the FEX stood up. So I have dealt with FEXs before, and they're okay. The problem is they don't learn anything. There's no, oops, it's supposed to be an N. There's no MAC learning at all. And up here is where the MAC addresses get learned. So if you have a traffic that comes in on this port here, it's got to get sent up here, get learned by the parent switch, and that traffic is going to get sent back down the trunk link to the port that it's going to go out, and then back out again. So there's no local MAC address table on the FEX. So, and you might say, well, what's the point of it? Well, the point of it was if you had a scenario where you needed more ports, almost 16 FEXs on a. Oh man, that's a lot, man. That's a lot of FEXs. If you had servers, server 1 through 20 that was getting deployed over here, but you didn't have any rack space for a full size 5K or 7K or whatever, you would run, some cables to it over here, and you'd deploy your FEX right there, and you'd plug them into your servers. That was the one and only. That was one scenario, and that was like probably 11 or 12 years ago when I first saw it, and it just a remote line card. That's what a FEX is. It was cool for the idea. Cisco tried coming out with the campus style design for that, and I'm trying to remember what it was called. Back when they came out with, was it the Cat 6800? They had something similar to that, where you would, and I can't remember the name of it off the top of my head. Such a long time ago. It did not take off. A lot of customers didn't buy it, but so yeah, it was an interesting design to say the least. So yeah, FEXs are fun to play with if you understand how they work. So let's take a look a little bit about the campus LAN, and actually let's look at the design guide here for SDA, because that was something you guys brought up last week, and how it comes into play. So SDA itself is kind of cool, and I'll talk a little bit about it at the high level. See if I can't find a decent picture here. It leverages VXLAN for its encapsulation for the data plane. It uses VXLAN. So I'll see if I can't. Well, that's actually not a bad example. Okay, we'll roll with that. Our security team always confuses me. They use the FEX acronym for FORTA extender, and I always get a brief moment of, oh crap, I didn't put them all out, or I didn't pull them all out. That's actually kind of funny. I had a customer the other day. How did he put something? And it was an energy company that I was talking to, and I was like, he made a comment about, I forget what the protocol was, and I'm like, are you sure that's what it means and not ICMP? And he's like, no, it's something else, and it's a proprietary protocol that's built into the system that they use to manage the power distribution that they support. And I'm like, oh, okay. Because I tried Googling it, and it came back with nothing. Very few research results. So yeah, I've been in that. I'm like, are you sure that's what you're talking about? So, yeah, it's good stuff, man. So let's see if I can't find here's an example of your R lock for your Lisp design. I'm going to go back up here. So let's talk a little bit about, and this is something that I see a lot of people struggle with, is the VXLAN concept and how it comes into play. Now, I'm not going to deep dive into how VXLAN works because I did an entire video series on that a long time ago. So if you want to know about, VXLAN, VTEPs, VNIs, and VLAN to VXLAN mappings and all that type of stuff, go check out the VXLAN playlist that I did on YouTube a while back. And I dove into that. And I've also done a lot of VXLAN since then. So if you have questions, throw them in the comments. But you have this underlay overlay relationship that you need to understand, where the physical underlay. We were just talking about this a little bit ago, where if you have a scenario where you need to have your traffic go this way, it jumps across the interswitch link and comes back up here to the other device. Well, that's how the physical network is seeing it. But the overlay, it looks like these two guys are directly connected to each other. So in a typical VXLAN fabric, you're going to have a spine 1, you'll have spine 2, you'll have leaf 1, leaf 2, leaf 3, and leaf 4. Now this is the data center example, but you're going to connect all your devices like so. And the intention with that is to provide not a full mesh, but a spine leaf architecture where no one device is more than 2 hops away from anything else. What I mean by that is 1, 2. And it supports ECMP, so equal cost multipath. So you have 2 paths to get from leaf 1 to leaf 2, or leaf 1 to leaf 3. And what this does is it gives you a lot of high-speed east-west communication, because typically these are going to be 100 gig links. And you can do 10, 25, 40, etc. southbound of your leaf. So there's a lot of capabilities that come into play with it. Now, what's cool about it is end-to-end, you have this thing known as the Anycast Gateway. And what is the Anycast Gateway? The Anycast Gateway is basically a floating gateway that you associate to all your SPI, all your VLANs, and all your SPIs. And the idea is no matter where your server sits, and a lot of times this is dealing with ESXi environments, so you're dealing with virtual machines. So you have your ESXi hosts sitting here, 1, 2, 3, and 4 respectively. And let's say there's 20 VMs per host. Well, if I move VM 11 from host 1 over to host 2, that's great. The IP address stays the same because the subnets are all across the board. These are all layer 2 adjacent. You can route between your VXLAN VNIs, which is referred to as inter-VNI routing, and all that good stuff with what they refer to as IRB, specifically symmetric IRB. And the idea here is whenever I have traffic, if I have VM 11 move from ESXi host 1 to ESXi host 2, it doesn't matter because the MAC address doesn't change. The only difference that changes is the MAC address now, instead of VM 11 being learned here, it's now moved over here to leaf 2. This updates the VTEP table. He propagates that information to the rest of the network, and then if anybody needs to get to VM 11, they know to point to 10.0.0.2 and not 10.0.0.1. And so all the communication between all your leafs, I'm just going to draw one big pipe between the 4 of them, is VXLAN encapsulated. Now that's within the fabric, right? All east-west communication, all that type of stuff. What if you want to get outside the fabric? You want to talk to the internet, or you have I'll draw it out a little bit here. Let's say we have a couple of leafs over here that have, we'll say leaf 5, and attached to leaf 5 we have 4 firewall 1, and we have load balancer 1. And then over here off of leaf 6 will be our edge, right? It'll connect to the outside world. And so we have our core, and then we have our WAN, and then for kicks and giggles, we'll say the internet. That's supposed to be iNet. Well, what's cool is you have all these connections going outbound. So if we have somebody come in from the core, all this communication on these links is all eBGP. BGP, there we go. And what you're doing is, if you need traffic to come in and out of the fabric, this leaf right here, leaf 6, and this leaf right here, leaf 5, they're configured identically to leaf 1 through 4. They're all going to be configured identically. The only difference is that they're not going to be hosting any hosts attached to them, right? They're just going to be used there for service communications and things like that. So if for some reason you need traffic to come into the core, or come in from the core, and there's a security policy that says that anything that's coming into the fabric from the outside, regardless of which leg of the network it comes from, you need to make sure it goes through a firewall, so it's inspected. Cool. And then if it's destined to web servers or anything else for that matter, it also needs to hit the load balancer so that the traffic is handled appropriately. Well, that's what they refer to as that's a horrible P, by the way, PBR. Actually, it's called enhanced PBR. And what you're able to do is you're able to send the traffic here, jump it over to leaf 5, who's able to pass it to the firewall first, then the load balancer, then the traffic gets back to leaf 5, and then goes to whichever leaf happens to be the device or the leaf switch that connects to that particular host or that particular virtual machine. And that is really the beneficial piece to VXLAN in a nutshell. So I've deployed this a bunch of times, and unfortunately, a lot of your whiz-bang wow capabilities that you would normally want to play with, they're not really supported on virtual 9Ks. Believe me, I've tried. I've had a successful rollout of this exact same design, and I take the config, I dump it into the virtual 9Ks, even the latest code, and it doesn't work. I'm told that inter-VNI firewalling, if you want to do like east-west inspection, I'm told that works. But I'm if you're staying inside your VLAN and inside your VNI, it does not. So I have not tested that specific piece out, but that's what I'm told anyway. So your mileage may vary. So what's cool about this too is you can do multicast inside of your VNI. It's what they refer to as tenant routed multicast. That's supposed to be an M, by the way. And you run it inside the VRF and all the good stuff that goes along with that. So that's a high level of how VXLAN comes into play and some of its operations. But the cool thing about it is it scales, right? I had a customer come to me. Actually, funny story. I deployed VXLAN like identical to this. Well, very, very, very close to it. Deployed it like this, and as I got done deploying it, and everything was working out pretty swimmingly. It was within a short period of time later that I got another deployment that came across my desk for, there was a hospital system in the southeast that they wanted to deploy VXLAN. I was like, okay, cool. Or they needed layer 2 extension support. I'm like, okay, well, this is, to me, is a no-brainer. It's going to be a VXLAN deployment because no one's going to deploy OTV or overlay transport virtualization. It does the exact same thing, sort of, but it's not as cool or flexible as VXLAN. So what we ended up doing, and I'm going to go ahead and, unless somebody has a question, can I scroll down a little bit? No, I need that white. I need the dark space. So if you guys have any questions on anything that I've covered about VXLAN, you can throw it in there, and I'm happy to go a little bit over on my my live if I need to answer them. But what I ended up doing with them, it was kind of a cool deployment actually. They had a HQ location, and then they had a colo location, and between they had 9K1, they had 9K2, 9K3, and 9K4. These guys are all VPC together. That's supposed to be a port channel, by the way. And talking to each other, all that good stuff. And the DCI going between the two was actually crisscrossed. I tried convincing them to change that so they were point-to-point connection, but anyway, that's a whole other story. And they had these guys, and I don't remember the exact specifics because it's been a while since I've done this deployment, but they had a core design down here. They had some routing up here that they needed to figure out. So I stood this all up in the lab, and it took a couple of weeks to work through all the details and get it all figured out and what needed to be configured and where, all that type of stuff. So anyway, long story short, we got it all rolled out, figured out all the internals, and then we stood up VXLAN between these two sites. But VXLAN only existed between these two locations. There was no VXLAN internally. So what it was, essentially what we ended up doing is what they call a multi-pod. Oops, that's supposed to be an L. Multi-pod. And the idea of multi-pod is two different eBGP peerings, and you're extending BGP between the two sites, and it's kind of interesting. If anybody wants to get into the specifics, I'm happy to talk about it. But when you start digging into the specifics of it, essentially all they needed to do was take a bunch of VLANs from here. So VLAN, let's say 100 through 300. I don't think it was quite that many VLANs, but it was a lot. And they just wanted to be able to pipe it over here to VLAN 100 through 300 and vice versa. Be able to go back and forth. So we stood this up. It was kind of a interesting design, but we got it stood up and we started rolling traffic. They started doing their migration. Well, and what was cool about it was they could just unplug something from the HQ site. They could drive it, the 10 or 15 minutes to the colo, cart it to the rack, plug it in, power it on, all that good stuff, and then within a few minutes, bada bing, bada boom, things were working. The beauty of layer 2 over layer 3, right? So that went swimmingly. They had everybody was happy. Now the interesting thing about it, and I think I've talked about this before, is they decided they want to take their firewalls that were here and they wanted to move them over to the colo. And so they set up another pair of firewalls. So they had firewalls here, which I think they were firepower boxes running ASA code. I won't judge them. And so they wanted traffic that anything that would normally hit this pair of firewalls would go over the WAN to this pair of firewalls, come back out, and go northbound out of their network, hit another pair of firewalls, and go out to the internet. That's what they wanted to do. I was like, oh, okay. So we made it happen. That was like phase 2 or 3. And so we got that done. And then they came back to us probably 3 or 4 months later, if I had to guess, and they wanted to add a third site. I'm like, okay, cool. So long story short, we ended up converting their 2 E lines to a single E LAN. So they added a third site, so another pair of 9Ks, 9K5 and 9K6. We joined these guys all to a big E LAN. Everybody was doing well at this point. And then we basically set up a bunch of VXLAN tunnels between here, here, and here. So we had a big triangle, if you will. And they were replicating between the colo and this other location, which was another colo site. And normally I would never have deployed that. Normally I would have pumped the brakes and been like, okay, yeah, that's not a great design. If you don't need VXLAN somewhere, you really should remove it. Because that's what I was going to do with the HQ site. I was like, okay, once VXLAN is deployed and stood up, we're going to rip it out of this other site because all you really need is to turn it off and just do BGP, routed across, right? We'll set up a default route to point you over to the colo firewalls. You'll hit them. You'll come back across the fabric, routed, and away you go. And I was basically told that what they had in place, everybody understood. Everybody liked it because they had layer 2 reachability. They didn't have to sit there and monkey with anything. And I was like, oh, okay, well, I suppose that works. So I said it's definitely not a best practice what we've put into play. And I would just be cautious when you get down to the details of, something fails over, and we did a lot of failover testing, but we got to a certain point where it was just like, huh, I don't want to get made fun of. It's not a best practice design, and so we were taking basically the data center interconnect portion. So if you're doing VXLAN multi-site between two different data centers and you want to do extension between the two, that's essentially what we were doing, minus the multi-site specific configuration. We never actually put that in. So that's essentially what we ended up pulling off. It got the job done, and the customer was happy with the overall usage of what they were trying to do. But it was just a very interesting design over at the end of the day. And that's why I was mentioning it the other day. I forget which video I talked about it, where you do best practice as far as you can, right? You take best practice as far as you can until best practice is no longer going to meet the customer's needs and demands. And even if you're advocating not to do something a certain way, if they have a business driver or whatever reason in order to continue to go that direction, well, that's what you're getting paid to do. So you put your personal opinions of what they're doing on the back burner and you give them what they want, as long as you're not doing something stupid like exposing a major security vulnerability or putting their firewall and permit IP any to just get traffic to pass through to go where they want it to go. You know what I mean? You don't do stupid things. And the problem with that, though, is it takes more time to figure out those niche configurations, which are not usually common to deploy. But that's what your job is as an engineer, right? So you spend 80% of your time figuring all that stuff out so that when you get to the 20% where you're actually deploying, that you can actually get it rolled out and it makes sense. So definitely an interesting architecture, to say the least. So if you guys have any questions on that type of stuff, let me know in the comments, or I should say in the chat here. But we're at the top of the hour. It's 8 o'clock my time. So if you guys, I know it's getting late for some of you, but if there's anything you guys want to chat about before I cut you guys loose for the evening, we can do that. If not, I will see you guys next Wednesday. Excuse me. For another Whiteboard Wednesday. This one was pretty successful. So hopefully you guys get on the bandwagon. I'm actually going to update my banner on my YouTube channel to say that we do 7 o'clock lives instead of Sundays at 2. So, but if there's nothing out, if nobody has anything, I will bid all of you farewell until next week. Don't forget we have the coaching session Friday night at 7. And I'm going to pick up where we left off with the firewall and router NAT configuration and do with IPsec VPN with NAT extensions. Or NAT exemptions, I should say. So, with that being said, ladies and gentlemen, assuming that there's a mixture of you guys out there, probably all guys, if I had to guess. I think women are like 1% are female. These deployment conversations are pretty cool. Well, I appreciate that, Irfan. So if there's if you guys don't have anything going on, I appreciate everybody stopping by and hanging out with me. This was actually a pretty good turnout. So I think the most concurrent views I had was like 16. So that was kind of cool. So anyway, I'm going to let you guys go since there's nothing in the chat that's saying otherwise. You guys have a good rest of your week. Stay safe out there. If you guys have any questions, let me know in the comments section below. If there's something you'd like to see, let me know. But other than that, I will get the Tech Support Thursday video out tomorrow sometime. And in that, there will be all the usual links, Patreon link to the membership if you can't get it via YouTube, the workbook, the